this is the answer. Tan of 2Ka plus delta. It's a little messy, no wonder. It just plotted these functions. Sine K prime A cos kappa A, a ratio, plus K prime over kappa cos K prime A sinh kappa A. You have sine K prime A sinh. The sinh and cos alternate. This trigonometry is the same, but this one changes. Same thing here, K prime over kappa cos K prime A cos kappa A. So it's a well-defined expression. If you know the number kappa A, you can calculate everything. Let me just make sure you can see that. If you set, for example, Ka, this is the natural variable. Ka is just, the K is related to the energy directly. So Ka has no units, call it U. Then you have two parameters of the square well type. A depth V0 and a height V1. So there's natural to define, just like you would have Z0 squared, which is 2m V0 A squared over H squared. You also define Z1 squared this time as 2m V1 A squared over H squared. And then the energy, we can do another thing. We can define the energy divided, say, by V1 to be little e. And that's reasonable because this energy is compared always with V1. And we've solved this problem in the domain when the energy is less than V1. And that's why we have kappas here. And if energy was bigger than V1, we would have trigonometric functions everywhere. Now, you can switch from trigonometric to hyperbolic by analytic continuation, letting an angle become imaginary. A trigonometric function becomes a hyperbolic function. Most of us are rather uncomfortable doing this at the beginning because of the matter of signs. If you mess up a sign, it's a big problem. But at the end of the day, it actually saves a lot of work. So a little of that in the homework you will see. But at any rate, this is valid for E in this range. And therefore, this ratio is H squared, K squared. You can put an A squared over 2m V1 A squared. And you can see a U squared here. And, I'm sorry, not there. A U squared here. And the H squared divided here gives you a Z1. So this is U squared over Z1 squared. A couple of extra things. I'm just putting it here because if you ever have the curiosity of doing these plots, this may help. K prime squared is related to the energy, therefore U squared, and V0 Z1 squared. That's C0 squared because of V0. And for the other one, kappa A squared is equal to Z1 squared minus u squared. So everything becomes a function of u. Wherever you have a kappa prime a, you have a square root of u. Now, somebody has to give you the values of z0 and z1. Those are the data of the potential. Z0 and Z1 are numbers, you know them. Therefore, you know kappa A as a function of U, kappa K prime A as a function of U, and Ka, which is U. Therefore, this equation becomes a function of U. You can use arctangent here and solve for delta. It's messy. There's no, remember I mentioned the other day the fact that you could do trigonometric identities and solve for tan delta here, but then this I don't think simplifies when you solve that. It becomes just a bigger mess. You did solve for tan delta, but it's very messy. So anyway, let's leave it there. Are there any questions in solving this problem? So in principle, we solved it. I didn't plot anything, so you still don't have any insight as to what's happening, but you've learned in principle how to solve it. Any questions? Okay, so let's plot things then. Maybe I should start here. Okay, I'll start here. Oh, if I'm going to plot, I have to choose things. So we will choose z0 squared equals to 1, or z0 equals to 1, and z1 squared equals to 5. So we put a big barrier there. And now let's plot delta as a function of Ka or u. Now from this equation, we see that u, little e must be at most 1 for our formulas to be correct. So u must be up to up to z1, because you must keep this ratio less than 1. So we can plot u up to square root of 5. 5 is 2, and that's it. And here we're going to plot delta of u. And here is minus pi over 2 minus pi. And so what does it do, the phase? There's no way you can guess, I think, from this formula. I could not guess from this formula. So we could try to imagine. It's possible to guess, actually, after you've solved this week's homework, you probably will have a good guess that the phase shift begins with minus 2 Ka, as if with very little energy you reflect back here. So there will be a shift that is calculable without doing any work. So it begins linearly, and it represents a time advance. So it goes linearly and negative. That's how it begins. Because for very little energy, it's going to bounce back. And you know that the delay is proportional to this derivative. So it must be negative like that. So then what does it do? It crosses this point, reaches almost pi, and here is what something quite remarkable happens. At some value u star, which is about 185 23, I think. That's what I calculated. let's see here. The phase that is almost minus pi suddenly jumps very, very fast, crosses pi over 2, and then, well, it seems to do something like this. I don't know what else it does because we have not calculated it. But it jumps very fast, almost a value of pi. Now, this is quite interesting. If you think of what we used to call the scattering amplitude, AS squared was sine squared delta. The amplitude of the scattered wave, sine squared delta. The amplitude of the scattered wave is going to be quite large here. It's going to be 1, which is the maximum. AS squared is here. So I want to keep these two blackboards aligned. So here it goes like this. It's going to go up like this, and do this, and broadly go down, and then very sharply go up, more sharply at least, go up again, something like that. So here it is. This point over here has a strong scattering amplitude, but there's nothing too dramatic happening here. This sign corresponds to time advance. The derivative is negative. And time advance cannot be too large, as you know. On the other hand, here is time delay. And time delay can be very large. So we think this must be the resonance, and this is not a resonance, even though the scattering amplitude is big here. So we continue here and plot the time, interestingly, the amplitude inside the well. So here it is. How does the wave function become through this constant inside the well? And indeed, this confirms that nothing very special is happening here. What happens now is some sort of behavior like this, and a big jump here, in which the amplitude apparently, I have not quite confirmed this number, is at least the value 3. But very large and sharp. I should have room for one more plot. Of course, the star plot of this thing is, I'll do it compressed here. The total delay, 1 over A d delta dk. Well, it begins negative. And remember that when we did the 1 over A d delta dk, this is a pure number. It expresses the delay in terms of the time that it would take to travel the inside region. So how many, if you would get a 1 or a -1, is just a delay that is of the size of the time needed to travel back and forth. So actually this goes a little negative at the beginning, you know, the derivative is like that, and when you plot this, you see that it's very sharp, and it's a value of about 14. 14 times gets delayed from what you would expect naturally of the time that it should have spent traveling back and forth. A gigantic time delay, a peak in the time delay, peak in time delay, peak in the amplitude inside the well.